students, welcome to this session on order statistics, which will turn out to be super important and interesting for auctions. Alright, so in this notebook, I'm going to give a numerical perspective on order statistics, which may or may not be more intuitive to you than the purely statistical, but should at least be complementary, or rather the asymptotic one. Alright, so we're going to be running with a number of simulated draws, and this is because we're going to simulate our way out of the expectations, taking averages of simulated numbers, rather. There's some theory on order statistics that you can look at here, but let's get started. And for the first example, we're going to do just normally distributed variables. We're going to be drawing them 5 at a time. We might think of it as 5 bidders, and we're going to repeat this exercise 1,000,000 times. So first off, let me just show you here. Here's a data frame. Actually, it might be more useful for you to look at a different data frame. Maybe let's try looking at it like this. So think about it like this. This is bidder 0, 1, 2, 3, and 4. So there are 5 bidders here, and here are the values. So each of these numbers here represents a replication, and we're going to be doing 1,000,000 of those. And so for each of our auction rounds, let's just print the first 3 as an example here. We could, for instance, take let's just do the maximum over the first dimension and print the first 3 columns here. So the maximum from the first one is 0.6805. That's correct. The maximum, the second one here is 1.4. All right, great. So this is what this is giving us here. V.max of 1 is the maximum number across all of these 1,000,000 repetition of our draws. And so we can start to think about what does the max look like. So if we take just any of the rows, they're all distributed random normally. So if we just take the first column, as you can see, this is just the first column, minus 0.7, minus 0.49. So that's just the first column here. We can, the histogram from that is going to be just our good old friend, the normal distribution, standard normal distribution. As we can see here, it is the bell shape. But if we instead take the maximum for each of these rows and ask, what does that guy look like? Then we can see that it looks like it's inheriting the normality. It actually looks like it's slightly skewed. It looks like this tail goes down a little bit faster than the other one, and certainly the mean is different. So that's what we're going to be doing. We're going to be asking the same thing. We could, in each of these rows, be taking the second largest number. So the largest is 0.68. The second largest number would be minus 0.53 here. And we could write those in a column and do histograms. And that's essentially what we'll be doing. And so here, what I'm showing you is the max and the min together in one graph. So first we do the maximum, and then we do the minimum. And so here they are together. As you can see, the mean is much more censored. There's more dispersion for the maximum. The largest value is more dispersed in general. Okay, so one thing we might do is we could take our V here and do a histogram for separately for each of our columns. And they would be looking exactly the same, each of them, because they're identically distributed. So if we, this graph here is just plotting them together, and they're right on top of each other because we're drawing 1,000,000 repetitions, so they're too similar. But if instead we sort our data set, so that now you sort, if we take just the first 3 columns here of it, it's sorted so that for each of the repetitions we have them in ascending order. So now the bottom one is always the maximum and the top one is always the minimum, and it's been done independently for each of the rows. For instance, so the first one here, you can see 0.68, that was the largest one. That one goes on the bottom. the smallest number was minus 0.7, no, minus 1.15, that's here. That's the first one, and minus 0.7, that's the second smallest, and so on. So U has been sorted, and it's been sorted separately for each row. So for this row here, we can see that the smallest value is minus 1.2543, and that's the first one, and this is the second smallest, and so on. So they're sorted separately. And now if we take U sort and just take the last row, that's the maximum. So if we take this one and do a histogram of this guy, that's going to give us the histogram of the maximum as we saw just before. And here it is in a slightly nicer one, so the extra code is just setting it up more nicely and doing it separately for each k, so each position. So 1, the blue here, is going to be the smallest number, it's the minimum, and the purple color 5 is the maximum. And so here it is, for as if n is equal to 5, we're drawing 5 samples. Here are the distributions for each of the 5 order statistics. The first order statistic up to the nth order statistic. Here they are separately. Of course they're shifted because the maximum is always to the right of the minimum. They are overlapping because of course this maximum here could not have come from the same sample as the tail here in the red, the observation that's over here. Of course that cannot be the case. They're the unconditional distributions. But this is what they look like. So this is how dispersed the maximum is, this is how dispersed the minimum is, and so on. Alright, and we can then ask, what about the location of the mean? The mean of the kth order statistic. And I've shown those in dashed lines here. The mean of the 5th order statistic is here. It looks like it's 1 point something. The mean of the 3rd order statistic looks like it's almost exactly 0, and so on. But we can compute those means for different values of k. We can use k equal to minus 1 and minus 2. That corresponds to the last and the second to last rows. So those are the max and the second largest. And we can do them for different sample sizes, 2, 3, 4, 5, 6. Of course not 1, because we can't ask what's the second largest number in a sample of only 1. But we can compute these. So what they're basically doing is for each value of the number of draws that we could want to make, we draw some random normals, then we sort them, overriding U, and then we take the kth row, which is either the last one or the second to the last, and we take the average. So that's computing the average of the largest or the second largest values in all of these realizations. And let's plot them and see what they look like. So for the normal distribution, if we only have 2 observations in our sample, we can see that the largest of the 2 has an average of just over 0.5 and the smallest of the 2 just under minus 0.5. It kind of makes sense, right? Because the normal distribution is symmetric around 0. And then the more observations we're drawing per replication are, the larger the average value of the maximum becomes. And we can see the average value of the second largest also grows. So that makes complete sense. The averages of the maximum and the average of the maximum and the average of the n-1th order statistic. The average of the nth order statistic and the n-1th order statistic. Those two numbers are very important in auction theory. So this was for the normal distribution, which I just used because you're probably familiar with the normal distribution. Now we're going to shift gears and use the uniform distribution, because when we're in an auction world, we tend to want to work with distributions that only have support on the positive real axis. So let's do the same thing that we did just before, but instead of np.random.normal, we're going to go np.random.uniform. So as you can see again, if I didn't sort the the valuation draws, the uniform draws that I took, if I didn't sort them, So you can see U is 5 by 1 million. And if I don't sort them, they are all independently drawn from the uniform distribution. So plotting them, the 5 rows together, they look identical, right? But if I sort them so that in each of the 1 million samples that I draw, I sort them so that I always have that on the rth position, the rth row is the rth smallest, then we are going to get a pattern emerging, and this time it's going to look much more interesting. So as you can see, for the uniform distribution, we can never get below 0, but as you can see, the distribution of the 0th, actually this isn't the, what I'm showing here is base 0. Let's do base 1 because that's what we're used to. If we look at the first order statistic, i.e. the minimum, we can see that of course it can't have mass below 0, so but it's bunched up against 0 and decreasing in such a fashion here. And at the top, the 5th order statistic, or the maximum, is similarly bunched up against the top of a point of the interval. The 4th order statistic, however, has this hump shape here. It's very rare that we see the 4th largest number all the way down here, but we do see it sometimes. It's much more likely that we have it appearing up here around 0.7, 0.8. And in the middle we have a more symmetric looking pattern. So those are the distributions for each of the 5 order statistics when we're drawing a sample of 5 observations. And we've repeated this exercise a million times to make sure that these histograms look pretty smooth. When we vary the sample size, just as we did before, we get this pattern here that the average of the nth order statistic starts out at what looks to be 2/3, and what's going to turn out to be actually exactly 2/3. And the second order statistic, the second largest, looks like it has an average of 1/3. And if we have a sample of 3, then we can see here that the second largest on average is a half. So that makes complete sense, right? We've drawn 3 observations uniform and sorted them. One is above, one is below, and the one in the middle is somewhere around the average of 0.5. Makes sense with this green one here being symmetric. And then when we get up here, we can see that the average value of the largest draw in those samples is increasing in the number of draws that we take. And that's the second largest. And the second largest is going to be particularly interesting in auction theory. All right. Then we had an analytic formula for specifically for uniformly distributed variables. And it actually turns out that if x is uniformly distributed, then the kth order statistic is going to be beta distributed. That's just a law of math. But that in particular implies for the beta distribution, we know what the formula is for the mean if we know the degrees of the 2 parameters of the beta distribution. If it's k, n plus 1 minus k, those are the parameters that index the beta distribution. They take those 2 values, then the mean is k over n plus 1. So in particular, that means that the order statistics are going to be 1 over n plus 1 up to n over n plus 1. And let's look at it for n equals 6 and do the calculations. Here are the simulated order statistics, which is calculated in this way. We take n comma r draws from the uniform, and then we sort them column by column independently, and we just calculate the average value of the numbers that are in the k minus 1th row, and the k minus 1 is to get to base 0. So this is calculating the average value of the kth order statistic, and this is the analytic formula that I'm claiming. And as you can see, the 2 numbers are very, very, very close. Afterwards, we can play with, if you increase r further, these two numbers are going to get closer to each other. If you decrease it, they're going to go further apart. Okay, and then a second thing we can do is, as I said, when x is uniform, the order statistics are beta distributed, so we can actually draw beta distributed random variables. So let's take some beta distributed values. They take some numbers, and then let's just plot a histogram where we take the kth order statistic, which is in row number k-1, and then we also do a histogram of these draws that we have from the beta distribution. So I mean, what's going on below is just a more pretty way of doing it, but here's a histogram of those draws of beta, and then we do a corresponding histogram of our sorted values, so the kth order statistic, and when we plot them together and insert some extra code to make it look nice, voila, the two distributions are perfectly aligned on top of each other, the simulated one and the analytic version, so to speak, the one where we've drawn it directly from a beta distribution. So that is actually true. So that's what makes the uniform distribution nice, and it's a good example to work with, because we understand how the order statistics behave, and hopefully this is giving you an idea of a different way of thinking about it, in terms of just drawing uniforms and selecting the kth largest one, or kth smallest one rather, and computing the averages of those. And down here we're looking at the full distribution of the kth order statistics. So those are order statistics, and the last thing that I just want to explain, which is going to be useful, is understanding how truncated distributions work. And what I mean by a truncated distribution is that it's, imagine a distribution where we throw away some of the observations, namely the ones that fall above a certain truncation point. And I think it's almost easiest to just look at what's coming out. In what I'm showing you here is one of those is just showing you a vector of normally distributed random variables, and the second one, we've deleted all the observations from V, where V did not satisfy this criterion, so V was above the truncation point. And the dashed line is indicating the point of truncation. So what this is showing you is that what's happening here is when we're deleting, this is a density, of course we've deleted observations, so U is going to be longer than V. We've deleted a lot of the observations in V, and when we plot the density in a histogram, what we can see is that the mass just is distributed around here. We can see it's much taller here. The distance between the two histograms is larger here than here, and that's kind of telling us that it's almost as if each of these points are multiplied by some number relative to down here. And that's actually exactly how it works theoretically. The distribution function, the CDF, is equal, or here it's the PDF of the truncated distribution, is some constant multiplied with the PDF of the non-truncated density. Which constant might that be? Well, you know that probability distribution functions have to integrate to 1. They have to have a mass of 100%. So when you delete some of the mass from the original one, then you have this remaining mass that sort of is now missing, and you sort of smear it out. So you choose the constant that you multiply with here, so that when you sum up all of the sizes of these bins here, all of the observations in the orange histogram, it sums up to 100% still. So that's how a truncated density works. And so the way that we can draw from a truncated density is that we can draw, as here, from the untruncated random variable or the untruncated distribution, and then just simply delete the observations that violate the truncation. Then we just have to, of course, draw more observations than we would have done otherwise. So if we want to reach 1 million draws, then we have to realize that some of them are going to be deleted. So we should increase the number of initial draws in order to reach this realized number of draws. But that concludes this video, and I'm looking forward to seeing you in another video in the future.